Thank you. Before I begin, I want to stop and collectively recognize everyone, of course, that Jason mentioned, but also Jason and Will. I cannot believe the idea of finding out 12 hours before game time that you have to have a new venue is like an anxiety dream to me in real life. It sounds so awful, and the fact that this is seems pretty pro. I mean, obviously there's a little duct tape with the Hangouts, but my God, what an accomplishment, and thank you. So, round of applause. Definitely be a good anecdote for everyone in this room, I think. That's what we live for, right, anecdotes? Actually, speaking of what we live for, so why are we here, That could get really deep, but I just mean in terms of monitoring. If you search for existential crisis on Google, this guinea pig is top 10 material, which I really like. But what I mean by this is why are we here in Monitorama? I think that there's a lot of ways to think about that. If this were easy, no one would care about it, right? This is not easy, what we're trying to do. That's why everyone here is thinking about it, and there's a healthy debate going on in these talks if you think about it between using statistics and automated things and events and logs and tracing and so on. So we're here because we need to get to why. That's the purpose of monitoring. This has been said over and over again in these talks, but I think it does bear repeating, and it's worth remembering. Monitoring must tell stories. If it doesn't tell a clear story, it's not working. That's the point. In your head, you have to have a story. You look at the monitoring, you hear a story. That is the purpose of monitoring. The more directly those stories describe why something is happening, the more successful your monitoring is. And this is all definitional. I don't think there's anything to debate here. There are a lot of debates about how to do that, but it's not debatable that why is the purpose of monitoring. The stories that we're telling, they got a lot harder recently, which is part of why I think there's a renaissance in monitoring right now. It's because the problem is getting harder, and human brains, they like the hard problems, the meaty problems, and so people are getting interested in this. We feel like there's got to be a way out of this. But let's talk about why it got harder. So we still need to tell one story. The problem is that the number of storytellers is growing rapidly. Microservices are here to stay. I don't think anyone's really debating that, I hope. But they did break our tools. Our tools were designed to tell stories about a single process, or maybe 3 processes or something like that. But processes where as every engineer at your company knew the names of all the boxes, and they knew what they did, and they knew their boundaries well, that kind of world. These processes were divided up into packages, and maybe there is some difficulty in going from package A to package B from a monitoring standpoint, but by and large, you were within a single process, and that encouraged a certain category of tooling. Those packages have been split into services. Of course, this is approximate, but you get the idea. If you used to tell a story by following the flow of control in your program, you still need to do it. I mean, the application semantics are still happening across these conceptual boundaries, but the story needs to cross those boundaries as well. So the first big problem is how do you tell the story about one transaction in a distributed system, especially remembering that everyone is moving to distributed systems and this is commonplace. How do you tell a story about that? Okay, so that's one problem. The other problem is that there's not just one of them, there's a lot of them, and they're concurrent. So this is the simple thing. This is how we're thinking about our systems and our brains. At least that's how my feeble brain thinks about it. I'm not smart enough to really think about concurrency in a sophisticated way. But okay, maybe we can model it a little bit more complicated. Okay, maybe they're just happening at the same time, so they're overlapping in time, but it's still not too bad. Well, that's not quite right because it's async and there are callbacks, and this diagram doesn't even do it justice. There's no forks and joins. So that's pretty bad. But really what's happening is this. So it's all async, it's concurrent, and it's distributed. And so each one of your stories is happening concurrently with thousands of other stories in every process. And these processes are forking and joining and telling their stories in one big jumbled mess. And somehow you need to tease out one story from the distributed concurrent system. So that is the challenge before us if we're trying to understand application level semantics, which we are, in the context of distributed systems, which we run. So I will do this in 3 chapters. In my mind, if you're going to tell a story in a monitoring system, the 3 levels are what, where, and why. And I think we have a really great answer for what. We all know this answer, metrics. They're awesome for what, really good. Especially if the what is something that you want to alert on or measures some like key KPI for your business, or the top level latency or something like that. It's great for that. As an aside, you can, I want to make it clear that metrics can be inferred from other instrumentation, but the point is that what you're getting out of your system is a metric describing something that you really care about. That's great. And so those are the whats of your stories. When you get woken up, hopefully it's because something bad is actually happening, and the something bad should have a metric associated with it. So that's the what. I do have a cautionary note about metrics, especially as we move towards distributed systems. If you have some kind of table stakes for what you want to monitor in every one of your processes, especially in a microservices architecture where every process, it's not just CPU and network, it's like your RPC framework has a bunch of metrics, all of your connections to other storage systems have a bunch of metrics on the client, your service mesh has a bunch of metrics. If you put all these in a dashboard, it's just information overload, and the signal noise is so low that you're stuck with so many whats that you can't make sense of it. The way I think about this is the following diagram. By definition, in an application, as far as a user perceives your application, there is a fixed number of things that the user actually cares about from a product standpoint. So here we're controlling, product changes are out of the picture here, but as you add microservices, there is not an increase in the number of user visible symptoms that should actually matter. Those are a function of the product, not a function of your system. That's how I think of it anyway. However, the number of plausible root causes for problems is growing super linearly to the number of microservices. I'm not going to lie to you and pretend I know what the formula is, but it's certainly the case that as you build out complicated microservice architectures, the interactions between the services have some n-squared-ish thing, and you don't want to be enumerating your root causes for a variety of reasons. One is that there are just too many, and you'll go crazy. The other is that when you're on call looking at a dashboard, it looks kind of like this. But the other one, which I'll get to, is that root cause analysis is really hard. This is from my company. I did this actually. I put this slide together this morning. I just picked some random thing that happened earlier this week. It wasn't good. It wasn't terrible. It wasn't good. We have a bunch of metrics dashboards too, of course. And so I took 8 screenshots sort of at random, just tried to fill this screen of this incident. Which one is the root cause? Anyone? I honestly have no idea. I have no idea from looking at this. You can't do root cause analysis by looking at this stuff. Especially when it's not 8 graphs, but it's like 100 graphs, which is commonplace. If there's a real honest God problem, you're going to see spikes everywhere, So you can't do root cause analysis looking at time series data. It's just not feasible. There are too many. Okay, so that's what. Let's talk about where. This is the classic distributed tracing story. Officially, the title of the talk is distributed tracing, how we got here and where we're going, or something along those lines. So this is part of the how we got here. I've been working on tracing stuff for a long time, and this is the problem that we really set out to solve when we got going with tracing. It was, that there's a problem, probably latency or errors, maybe at the top of your stack, and you want to know where it originated. That's actually a pretty big step in your storytelling journey of figuring out why, especially if you have hundreds of services, figuring out which one is actually the root cause, even if you don't know why, that's a big step. So that's what chapter 2 is about. So again, metrics, great for symptoms, nothing wrong with using them for symptoms, but distributed tracing is a wonderful way to get to the where of a latency issue or potentially a user visible error that's originating from the depths of your system. wow, the font for the presentation is different than my normal font, but I want to introduce Donut Zone. This is something that I've built for this purpose. We're really going to push Murphy's Law today with the relocated conference and the Google Hangouts presentation and live demos, but here we go. So Donut Zone, it's blitz scaling, it's big, it's getting bigger, it's microservice oriented, and it's having lots of problems. It also is built using open tracing. One of the things I want to emphasize about this demo is that the instrumentation here is like really boring. It is not hard, and it's pretty much automated. So there's nothing you'll see today that involves anything interesting from an instrumentation standpoint, except for one thing, which I will talk about, but it's an isolated change. Let's talk about the architecture a little bit. So move fast and bake things. We are taking orders, and there's also clients for admin, like portals for stocking and cleaning the oil machine. There's a BrainPal payment system that we call out to as a SaaS. And then there's some services in the back end that fry donuts and top them with sprinkles or chocolate or whatever. So this is a basic architecture. The goal here is to make something that's complicated enough that we can all kind of, there's suspension of disbelief that this is an actual microservices architecture. Obviously, they get way more complicated. I want to highlight that, like all systems that do anything even remotely interesting, there's some issues here. The issue in this case is that we can't restock the sprinkles and apply them to the donuts at the same time. So there's a mutex there and a queue that blocks behind the mutex. And in the fryer, similarly, you can't fry donuts and clean the fryer at the same time, but we do need to clean the fryer. So again, we have a queue. Now, in a real distributed system, these things would be like database tables, or maybe there's a producer-consumer queue within a process, or maybe it's a producer-consumer queue like Kafka, or maybe it's a network link or CPU on a machine. All these resources are things that can become bottlenecks, but we have two that we're focusing on here. So I'll show you how this works. I'll order some donuts. I'll go to donut.zone, my browser, and okay, so here's some donuts. Looks like we've got some sprinkles, cinnamon, and chocolate. These are the three types of donuts I've got. I'm going to order a bunch of donuts, and you can see as I order them, I await them down here, and we have some timing information. Maybe it's a little hard to see. I'll make this a bit bigger. And yeah, okay, so they eventually fade away. And there's some inventory information up here about how many of these different types of donuts we actually have, and indeed, if I order too many, I will run out, and there are no more sprinkles. Okay, so that was pretty basic, but simple. I can also restock donuts if I'd like to. I can restock cinnamon, and you can see the inventory is increasing. I actually want to restock a bunch because later on we're going to be eating a lot of donuts. Okay, great. So let's go and look at some sprinkle ordering in a tracing system. So here we go. Here's a bunch of donut orders. I will just pick this one at random. And this is a distributed trace. So you can see it's originating in our browser, get donuts in the browser. We go to the web server. The web server calls this make donut function in another service. And then the make donut function fries the donut, processes the payment, and sprinkles it with something. Okay, so timing diagram, wonderful. That's important to understand that frying is on the critical path here, and so that's where we should optimize if we want to make things faster. You can see I've really beefed up the inventory. So you saw the critical path. Did that make sense to people, or general nodding of heads? It's not that complicated. Here's another one. I'll just walk through this one too. Get the donuts. Here you can actually see some latency in the Wi-Fi. And I order the donuts, it makes the donuts, and then we go through, process the payment, fry the donut, apply the topping. This is the way this system works. Now, that's great, nothing wrong with that. But there is something wrong with that. So, it's good to know that, where is this trace? That this fry donut span, this is the one that is holding up the transaction. And so that's the where. We got to the where. And I assure you, if your system had 100 services, getting to the where would be a big deal. It's like, great, you know, now we know that's where the problem is. And we do know that. That's where the problem is. That's unfortunately not the same thing as why that was slow. And this is where distributed tracing's dirty secret, is that you can get to the where, but that isn't the full story. You have not actually root caused your problem. So let's talk about that. So why tracing is hard. So this is why we didn't solve this already. There's lots of data. Charity's talk, which I really enjoyed yesterday, spoke to the fact that instrumentation is not the same thing as data. The tracing instrumentation, in theory, is a really magnificent data source. It has not just timing information, but key value tags and causal information for your entire distributed system all the time. And when we were at Google designing this stuff, we ended up, by the time we were done getting to durable trace storage, we'd thrown away 99.99% of it. So we sampled 1 out of 10,000 traces, and the other 9,999 we literally discarded. So it's a lot of data, but by the time you actually get to trace storage, it gets cut into like a, you know, into this just sliver of what you started with. Let me talk about where you might do this sort of sampling. The first place you would do it is in the process itself. The instrumentation might not even turn into an in-memory data structure. So that's the first place you can do it. The next place is between the process's buffer and some kind of other buffer, whether it's a file on disk or some kind of collector process running on localhost or a collector process running in your VPC or in a SAS or something like that. That's another place you can do sampling. And then finally, you can do sampling at the very end before you write to durable trace storage. Now, with Dapper, what we were actually protecting was the cost of the system in durable trace storage. That was what we were actually protecting when we chose our sampling parameters. And we wrote this white paper. It was a funny anecdote. So we wrote this paper about Dapper, which people have read apparently. I mean, that paper got rejected by every conference I ever submitted it to. I submitted that to like multiple conferences. No one would publish it. And there's nothing of any scientific interest in the paper whatsoever. It's like all like totally old news. And the only thing about it that's interesting is just that it existed and we had some parameters for how to build the system. Unfortunately, the parameters like this 1024 number or the 10,000 number, they're in the paper, but I don't think we did a great job explaining that. The 1024 was not to protect your process. You actually don't need to do sampling in your process for almost any real system. I mean, the amount of data that's coming out of the process, if you just ship it off, those numbers were taken like 2004 at Google, which is a long time ago in a very weird place. In the real world, you don't need to sample in the process. Like, you just don't need to. It's not necessary. So you've thrown away like a huge amount of data, and as I'll get to later in the presentation, data that's a lot richer than I think we even realize in this industry right now. You've thrown it out before the game even began. It's an incredible mistake, like a really, really big mistake. Okay, and then the rest of the sampling was done to protect the cost of running the tracing system, which is a real thing. If you take all that data and write it to disk, if you wrote it to Splunk or something, which is admittedly a very expensive product, it's just like mind-blowingly expensive, so much so that you would never do it. So there's a cost problem on that side too. But what I'm here to say is that these first two sampling cuts are actually unnecessary from either a performance standpoint or a cost of goods sold standpoint. You can record all that data. It's difficult. It definitely requires some thought and careful system architecture, but you can do it. And that opens the door to some very powerful things. And that's what the rest of this talk is about. So, all right, so distributed transactions are not independent, okay? They're really not independent. And the corollary to this is getting into the why, is that I have a hypothesis that almost every latency issue that you ever care about is actually a contention issue with something. It's either, again, contention for CPU, contention for memory, contention for a database table, contention for a queue. It's contention. And that is the source of all latency problems. Or if not all, very nearly all of them. Okay, so think about that for a little bit. So in my mind, the real problem we're trying to solve, if we're trying to get to Y for latency, is to understand contention in distributed systems and to do it in a way that doesn't require a lot of forethought. Getting back to the enumeration of all root causes, you don't want to specifically measure every source of contention and diagnose them independently. You want a general purpose mechanism to diagnose contention in distributed systems. So this is a way you could do that. Let's imagine that you have tracing instrumentation, and let's further imagine that when you traverse a resource, whether it be a process or a mutex or a database table, that you assign a totally pseudo-random, doesn't matter what it is, identifier, globally unique identifier to that resource. So this is something that would be done in like a mutex wrapper library, which is what I've done in the demo you're going to see, or it could be done in like a database RDB, like a JDBI kind of thing, or it could be done just at the process layer. This is not difficult, and it would be part of the abstraction layer for whatever system you're using. Or if it was an RPC system, it could be around the service that you're depending on. But you assign IDs to things that you might contend on in the distributed system, and you tag spans with that. Getting back to another excellent point from Charity's talk yesterday, this idea that cardinality is a problem is unique to systems where you do your statistical aggregation preemptively, which is what happens in metric systems. This would be really bad news if those contention IDs were the values on a metric aggregation. And there were talks yesterday as well. I think Aditya's talk, which I really enjoyed as well, I think spoke to the problems that you can have if you try and use a high cardinality thing like a contention ID as a value for metrics. But what I'm saying is that for distributed tracing instrumentation, it's totally fine. In fact, I would say it's good to put the contention ID as the value for a tag, because there's no issue with cardinality. We're talking about event data. There's no issue with cardinality. And I'm further going to say that these contention IDs can lead us to automated root cause analysis. And to me, that's really, really exciting, and I think is novel. I would actually love for people to come up to me after this and tell me I'm totally wrong, as I want to study how other people have done this automatically and in a general purpose way. But I think it's pretty interesting. So let's talk about this in pictures, because this is really important. If there's one slide you actually pay attention to, this is probably a good choice. So we've seen these timing diagrams before. It often looks something like this. You have like a parent span and a bunch of child spans. A span just being a timed event in a tracing system. There's like a natural critical path that comes out from these diagrams. We saw earlier, like this thing right here is presumably the critical path that's blocking the parent span. So the question is, what is it contending on and why? So if we had a contention ID, let's say this is blocked on a mutex, which is what ends up happening in donut zone. If this had a contention ID tag, what if we could say, in the distributed system, what if we could say, I want to know every other span in the system, not in this trace, but every other span in the system concurrently that's also contending for that resource. So what if we could issue that query and actually get the results with perfect accuracy? Here they are. Here's these spans that are contending for that resource as well. So the question is, where did they come from? Because that's your answer. If you know where these came from, you know where the contention is coming from. That's like a really profound thing. Okay, so you've gone from knowing your system was slow, which is definitely good. It's good to know it's slow, and knowing where it was slow, which is also good, to actually having a potential answer to why, which is to say, these are the contending spans, where did they come from? So we can do that. Like, we have the causal information. We know exactly where they came from. They each have a parent ID, so just walk the graph, figure it out, and you're done. So like, now you actually have a real answer to this problem. You were contending on a resource, you figure out what else is blocking on that resource, and in that particular time interval, no less, right? This is reduced to this time interval, and figure out where those things came from and do aggregation on that. So what would that look like? Okay, so this is enough slides. Now I'm going to really push Murphy's Law to the max and ask everyone to get your phones out and go to donut.zone on your phones Or if you have a laptop that's tethered, that's fine too. Don't do anything yet, please. Don't cheat and read the slides. This is a delicate. The chances of this working are double digits percents, I think, but that's all I can say about it. Okay, so hopefully people have arrived at donut.zone. What we're going to do here is split the room in half. There's going to be this half, I'll call this the right half from your standpoint, and the left half. And you all are going to be group A, and you all are going to be group B. And what I'd like group A to do is to just start ordering any old donut that you want, but not too many, okay? Don't go nuts. And then group B, I want you to order sprinkles. Go. So group B, just hit the sprinkles button. Group A, order miscellaneous donuts. I'm going to go and check out how things are going. Inventory is going down quickly. This is actually very impressive. You guys are fast. Wow, this is awe-inspiring. Okay, that's good. Stop. This is amazing. I can't believe. So the fact this has even worked this much is like almost a bit of a surprise. So let's look at some of these sprinkle orders. Oh, they're taking a long time. So first of all, let's just talk about how crappy it feels to use a product that doesn't respond quickly, right? 8 seconds is a really long time. It's like an eternity when you're on a device. And yet, like, a lot of websites routinely render pages in that sort of time frame. So I'll open up one of these 8-second traces. It's going to retroactively assemble this thing. You can actually see the network lag here is significant because this is mobile. There's a while before we even got to the server. But again, you know, we order the sprinkled donuts. There's a make donut thing. We process the payment, and then we fry the donut. Frying the donut, this took a long time. In fact, it took all the time, really. It was like 250 milliseconds waiting. This is kind of hard to see, huh? 250 milliseconds processing the payment on BrainPal or whatever. But frying the donut was 8.7 seconds. That's the problem. That's what we'd like to understand. So let's figure out where the load came from. So here we've done this analysis in real time, okay? So here's fry donut. It was called by make donut, but you can see the sprinkles is the critical path here. Not critical path, sorry. Sprinkles is the problem, okay? So you can see this is a backtrace of 100% of the data that overlapped with that particular 8-second interval, okay? And then we're looking at those backtraces and summarizing them. You can see that the other people who are ordering chocolate donuts, and there's actually a background robot that's always ordering cinnamon, just loves cinnamon donuts. And then we have some other people ordering cinnamon donuts, some real people. But 90% of it came from sprinkles. That's really powerful, right? I mean, so now you know that this latency that we're experiencing is due to sprinkles. And what's cool is that if I go and look at chocolate orders, I have a bookmark for this, we'd see the same thing. So the chocolate stuff was actually pretty, relatively speaking, was not that contended, but we'll get the same end result. Again, sprinkles are the problem. So it doesn't matter how we got here. So if you imagine these are two totally separate features of your product, but you're having latency of something, it's usually not that thing. That's the thing that's so frustrating about our job, right? It's like the problem is the other team that's like, you know, dominating your shared resource. So what if it just told you? It's like, it was slow? This is why. Like, it's right there. So the data's there. We instrumented it. We already instrumented it. It's there. Like, what a feast that we're leaving on the table, right? And there's nothing preventing us from doing this, except doing it. Okay, so that's round one. Let's go to round two. Now everyone on this side, just order whatever donuts you want. We've run out of some donuts, so I'd like everyone on this side of the room to go to the restock tab at the bottom of this thing. I'll do it too. And just, you know, start restocking stuff. You know, don't go, every time you click it's 10 donuts, so you don't need to go nuts or anything. And we'll do a little bit more restocking. Yeah, supplies are increasing. This is probably enough. You can stop. Wow, look at that. That's impressive. So we've got a lot of inventory. So let's see. We'll pick cinnamon this time. So I'll go and look for order donut cinnamon. And wow, these are taking a really long time. So let's figure out why. I'll click on any one of these, doesn't matter which. We'll assemble this thing. Oops. I knew something would go wrong eventually. Hold on a second. Let's see, I'll do a couple. Here's like a 4-second one. Okay, so now it's interesting. Now the critical path, we do see a lot of contention around, frying still, and it's coming, oh, someone cheated and went and cleaned the fryer. I didn't say to do that. Don't do that, you're scooping me. But anyway, so you can see now there's a pretty even distribution of people frying, so there's no clear culprit here. But when we look at the sprinkling process, we can see we're only contending with restockers for cinnamon, which is interesting, which is what you'd expect actually, because the different toppers were sharded, and so we only contend with transactions that did this. Now, I want to be clear, the instrumentation for this, it's just a class called smartlock.go, doesn't know anything about any of this stuff, none of it. The only thing I did here was to add a contention ID to the lock, that's it. Okay? And we can get this interesting interference effect between restocking and ordering, and we can see it just naturally. And you can see how the shards line up and so on, and where the contention comes from. So to me, again, that's a pretty powerful thing to know, that the live get donuts are contending with just the cinnamon restocking. And, oh, 1 minute? Good, I'm almost done. Last demo. We're greasy, okay? We need people to go back. I'd like the same arrangement from before, but can I ask you to go to the cleaner and just hit clean a bunch of times? Okay, great. Just get started. Okay, everyone go nuts.
Wow, this picture.
Oh yeah, it's a gross picture. I'll show everyone see. So only one person cleaning. Here's the cleaner. Okay, that's great. And now I'll stop. I'll refresh this thing. I hope this worked. It's not totally guaranteed that it did, given how many people are doing this right now. Wow, people are really going nuts. The thing I didn't expect for this demo is just how many people, maybe I'll look at the clean fire just in case. But yeah, if I look at the frying latency, well, yeah, it was a little unimpressive actually, because there's so much latency from other stuff. But this is supposed to take like a really long time to clean. And if it had taken, there's a circuit breaker in the code in case latencies got too high, just so people didn't like time out, and it triggered here. So bad programming error on my part. But if this cleaner had taken 10 seconds, even though only one person was doing it, you would see that here. So it only takes one request to bury everyone's latency, and you can catch that in this sort of setup. Okay. Anyway, what I was here to say was that we have to get to why. Latency is actually contention. And that tracing of the future, which is basically now, can do this automatically. Thanks a lot. Oh, last thing, if you want to talk more about this, I'm going to have a Birds of the Feather breakfast tomorrow morning at 8:30. Just send me a message on Slack. As long as you do it before 3 p.m. today, I'll add you to the invite, and it would be really fun. We're just going to nerd out about this stuff. Thank you very much.